Hello, welcome to software testing methodology. So today we are going to discuss about the topic is graph matrices and applications. So why we use graph matrices? So what is the main need of graph matrices? So every state graph defines some of the inputs, some of the outputs, transitions and some of the state bugs and transition bugs. That all represents in the graph matrices. Mainly this graph matrices used to calculate the mathematical calculation. If there is any mathematical calculation such as program code or source code, then in the software testing, we'll use these graph matrices to be tested as in the matrix way. So how the matrices is going to be tested and what are the applications now we'll see. So first, what is the motivational overview of this graph matrices means? The pictorial graphs are represented using another notation. It is known as the graph matrices. So the concept of graph matrices have been evolved in order to solve the problems of pictorial graphs. So graph matrices are used for proving the theorems. So I already told that if there is any theorems in the mathematical approaches, in that cases, we go for the graph matrices is used to for proving. The graph theory contains basic toolkit of three algorithms. One is multiplication, like a matrix multiplication. So second one is partitioning algorithm and matrix determinant. So these are the three graph theory toolkit which is uses these three algorithms to perform the graph matrices in the software testing. So if there is any mathematical calculations, if there is any theorems to be proved, in that case we will go for the matrices, graph matrices in the software testing, and based on the three algorithms, one is determinant, another one is partitioning and another one is multiplication as a matrix. So this is about the graph matrices. First we'll see the applications of those matrices. So applications where the matrices is used. So matrices are used when the programmer codes or encrypts a messages. So whenever the encrypts, nothing but conversion. If there is any conversion of input code to define to implement the output, so there the matrices in the theorem proving will be used. So geologists makes use of matrices for seismic surveys. So this is one of the way of application. And when in computer animation also we'll go for the matrices, and it is used for computing in architecture also. And math reports are recorded using matrices in engineering purpose, and it is used to calculate the gross domestic product in economics so that the goods can be produced more efficiently. In these are all the applications where these graph matrices used. Will use to encrypt images. In geologists, all the geologists will be used to for seismic surveys and computer animations, computer architecture, and recording matrices like math reports or producing economic some financial way. All the applications will go for the graph matrices in software applications. So, so in this, first how we'll use. First, we can define before using. We have to define. We have to know. We have to gain some knowledge about the matrices in software testing. How it will use. So to define that, first, what is meant by matrix of a graph? Define the matrix. The another notation of representing a graph is known as a graph matrix. So how we can say like state graph, flow graph, data flow graph, transaction flow graph, transition flow graph. Also here also there is a graph matrix, nothing but which defines a representing of a pictorial representation of a graph. So each and every node in the graph is represented as single row and a single column. Row and column. By using the rows and columns, we represent the graph matrices. In the state graph, we are using the nodes, links and loops. But here in the graph matrices, we use the rows and columns. Only single row and single column based on the matrix size. If the size of matrix is 2 by 2, that is a 2 by 2 matrix. If the size of matrix is 4 by 4 or 8 by 8, whatever. So that is defined based on the size of the matrix. Some examples I am showing here. See that examples. So first A. The node defines A 0. So A with a self loop, A will be link representation A. So A self loop, B, there is no reachable, it is unreachable state because, so there is no reachable means we will define the matrix like with a row and column like A. So here there is a transition like A, B. So A comma B. So this is the flow graph, small flow graph which defines the matrices. See this A, and this is a parallel link like this is parallel link which defines B plus E. So this is the B plus E and C and D. So this is the small graph matrix which defines this flow graph will be converted into graph matrix. This is known as a graph matrix. After conversion of in this graph matrix, then the software testing will be performing on theorem proving or in some of the applications like calculation of mathematical calculations. So this is the matrix of a graph. Next, coming to the simplest way to represent whether the condition exists or not exists between the nodes is binary weights, that is represents as 1 and 0. So the arithmetic rules for binary weights, arithmetic rules, addition, multiplication, 1 plus 1 is equals to 1, 1 into 1 is equals to 1, 1 plus 1 is not equals to 2, it is equals to 1 in arithmetic rules of binary weights. 1 plus 0 is equals to 1, 1 into 0 is equals to 1. 0 plus 0 is equals to 0, 0 into 0 is equals to 1. So you see here 1 into 0 is not equals to 0, it is 1 as our rule to be followed in the matrices. So it is a simple weight and connection matrix. So this is the simple weight and connection matrix. Next, coming to the principles, what are the principles to be followed in graph matrices? The first one is size. So size should be defined where the number of rows into number of columns should be equal to the number of nodes. How the nodes, like 5 nodes. So 5 nodes, based on the 5 nodes there is a 5 by 5 matrix. Based on the 3 nodes, 3 by 3 matrix. Number of rows and columns is equals to number of nodes in the flow graph. That represents the matrix, graph matrix. The direct link or connection between any node to any other node can be put in the matrix. The entry at the intersection of the row and column is the weight of the link that will connect two nodes in represented direction. So this defines the entry at the intersection of rows and columns, nothing but combining of weight links of the rows and columns. So this is one of the principles to be followed. If there are any more than one link between the nodes, which are known as parallel links, adding those links and performing the weights of those links as a parallel links. So that is nothing but principles. So next, coming to the flow graph example, the matrix is represented by the weights which are defined as above as a connection matrix with zeros and ones. It is known as a connected matrix, 1 plus 1 or 1 into 1, 1 into 0, 0 plus 1, whatever. The example of a connected matrix can be defined if this is the flow graph. So this is the example graph which defines. So this is the flow graph I have taken. See this. So A, C, these are all flow graph. Next, this flow graph is converted into graph matrix in this way. So this is the relation matrix. First we have to convert the flow graph into a relation matrix. Then it is converted into connection matrix. So A in the flow graph, A to C, capital A to capital C, the connection is A. In the flow graph, capital C to capital B, the connection is D. And capital C to capital D, connection is B. So then defines this all the matrix, and wherever the link is represented, keeping that link with the binary value as 1. So C1, 1. Rest of all 0. So that is the relation matrix and connection matrix. So this defines the relation matrix and connection matrix. So same, I am again defining the picture. What I have shown, the links of the figure are represented as 1, and if there is no link, it represented as 0. So the entries in each row represent the links from the corresponding node, and entries in each column represents in links from the corresponding node. In links and out links. There is a in link which takes the input from some other where there is outlinks which given to the transition to the another node. The different nodes such as branch node, junction node, loop node in connection graph can be identified as branch node, loop node and junction node. If the row contains two or more ones, then it is known as a branch node. In the flow graph, what I have shown as an example, in that flow graph there is a row C, D, E in the above figure or branch node. So the number of decisions at particular node can be calculated by using n-1 formula. If the row contains two or more ones, not one, two or more ones, it is known as a branch node. So like if you take the C node, C, D, E node, 2 minus 1 is equal to, like n-1 formula if you apply, 2 minus 1 is equal to 1, 2 minus 1. So all can be defined as a branch node. Next, coming to the junction node, if the column contains two or more ones, then it is known as a junction node. Column, if the row contains it is known two or more ones, it is known as a branch node. If the column contains two or more ones, it is known as a junction node. The columns B, C, E in the above figure are known as junction node. So loop node defines if there is any entry 1 in the diagonal of corresponding node, then that node is a loop node. So node E is known as a loop node. So if there is a diagonal representation, it is known as loop node. So this is about nodes, and next one is relations. So relations, you are well known about these relations. In the mathematics we have seen this. A relation is nothing but a property that connects any two things. If A and B are anything connected by relation, so it is said to be R relation to B, or relation ought to be A relation A or B, A relation to B. It is symbolically represented as A capital R B. So I already told that. So what are the properties? Transitive property, reflexive property, symmetric property, and antisymmetric property. So what is meant by transitive relation? If there exist two relations A are B and B are C, then R is said to transitive. So I am showing this here. See this. This is the transitive relation which, like A are B and B are C, is equals to equivalent to A are C. If A is equals to B and B is equals to then C, then A is equals to C. It is a transitive property, transitive relation to be satisfied by our graph matrices. If A greater than B and B greater than C, then A greater than C. So this is the transitive relation. Next, coming to the reflexive, the name itself tells the A reflection to A. So same whatever the variable we have taken, it is reflexive to same itself, like A or A. So then it is related to the reflexive. A is equals to A, or A is equals to A is not equals to A. It is irreflexive. So symmetric. The name symmetric is nothing but A or B implies B or A. Vice versa. A equals to B is A equals to B is equals to B is equals to A. Symmetric relation implies that if there is a link or connection between two nodes, that is from A to B, and there should be a link also from B to A. So such type of relation is known as a symmetric relation, and the relations which are not symmetric would represent a direct graph. The graph which symmetric relations is known as undirected graph. So this is about, see the example, like A is equals to B, then B is equals to A is symmetric. If A greater than B, then B greater than or not equal to A, then it is not symmetric. So that is the symmetric relation. Next, coming to the antisymmetric relation. If the relation A are B and B are A implies that A is equals to B. Still, it is known as an antisymmetric. A is equals to B, then B is equals to A, then A is equals to B. So it is a symmetric. If A greater than B and B greater than A, then A is not equals to B. It is not a symmetric. So this is the antisymmetric relation. Equivalence relation, the relation which satisfies these properties. Which properties? Reflexive, symmetric, and transitive is known as the equivalence relation. If the property satisfies the reflexive, transitive, and antisymmetric, it is known as a partial order relation. So this is about the relations and about the graph matrices and its applications. So hope you all understand about these relations, which is known as the graph matrices, relations, power of matrix, whatever. So this is about the graph matrices and its applications. So hope you all understand. Thank you very much.